So let's look at one more example of the Poisson distribution. And this is one that you'll run into in virtually every textbook. Usually it's the first example. Suppose we have a particular intersection in a town, and there's a average number of accidents of, say, 8 per day. Can we use that to find the probability that there will be 6 on any given day, that there will be fewer than 5, etc., etc.? The reason this example shows up is that where it fits the Poisson distribution very well. There is a fixed time period per day. There are an extremely large or infinite number of trials per day, meaning a very, very large number of cars coming through the intersection, probably in the thousands, depending on the town. And there aren't really all that many accidents in the course of a day. In fact, I want to change this a little bit just to illustrate. Let's change that to 6.3, just to illustrate that even though our individual number of accidents per day have to be a whole number, the mean does not have to be a whole number. The average can be something, a fraction or a decimal. All right, so we have our fixed time period. We have our large number of trials. We have a constant probability for each car coming through the intersection. I don't believe that's actually true, but as I said last time, we don't really care about that. And we have a fairly small average number of successes. Perfect example of success not necessarily being a good thing. So to find the probability that there will be 6 on any given day, that's a nice whole number. So we would do Poisson PDF 6.3 comma 6, right? We always give it the mean first and then the number we're asking about. So we would go Poisson PDF 6.3 comma 6, and it should be high, right? Because the mean is 6, so that's going to be, or the mean is close to 6, that's going to be the most likely outcome, about a 16% chance. Now, what if I want the mean that or the probability that there will be fewer than 5? We would use CDF for cumulative. We would give it the mean, and then remember it's always less than or equal to this number. Less than 5 is the same as less than or equal to 4 when we're talking about discrete probabilities, because we can't have anything between 3 and 4 there. So we would go to Poisson CDF 6.3 comma, and we want less than or equal to 4. About a 25% chance that we have fewer than 4 accidents or fewer than 5 accidents on a given day. And then one type of question we haven't really looked at yet, not in the videos here, we will in class for sure. What about the probability that we have more than 10? Well, if you think about the possibilities, right, or they're on a number line, we can think of them as being on a number line, and we got 10 right there. Well, the probability of having more than 10, that's going to be those on up to infinity, right? Which means not up to and including 10. More than 10 means not less than or not equal to. So we would use CDF to find the probability up to or equal to 10, and then we subtract that from 1. And so if we do Poisson CDF 6.3 comma 10, we get 94.4%. 94.4% of the time we'll have 10 or fewer, less than or equal to 10. If we subtract that from 1, we get 5.6% of the time we would have more than 10. Okay, just a matter of button pushing, very repetitive, nothing different from what we've done with the others, the other types of distributions. Let's look at our range of likely outcomes. We know our mu already is 6.3. We know our standard deviation is going to be the square root of 6.3, which is 2.5 almost exactly. If you double 2.5, you get 5. Subtract that from 6.3, you get 1.3. Round up to 2. add 5 to 6.3, we get 11.3. Round that down to 11, right? Range of likely outcomes. We always round in as opposed to up or down. So we can expect that 95% of the time, we're going to have somewhere between 2 and 11 accidents at this intersection. Or you might think of not the intersection, but the whole town, probably more likely, depending on the size of the town, that the number of accidents in the entire town would be a small number like this. Now, why would I care about this? I'd care because I want to be prepared for this many accidents. Right? If the likelihood is that I'm going to have this number of accidents, I need to make sure that I have sufficient emergency personnel, sufficient 911 structure and whatever to handle up to 11 accidents. And I also need to be aware that about 5% of the time we're going to have no accidents or one accident, or maybe 12 or 13. So I definitely want to make sure I've got another district close by that I can call on to help in those instances. Right? And that is the end of the Poisson distribution.